Okay, welcome to the first class meeting of EECE574, the graduate level probability and random processes. Usually in the first lecture, I will overview the syllabus and perform kind of course administration. But after serious consideration, I've decided to immediately start the coverage of the course because we need to review the undergraduate level kind of prerequisites first, and it seems that we have a lot to do. So here goes the review part of chapter 1. And this lecture note handout is based on our undergraduate level probability and random processes, which has title EECE302, the Mathematics for Electrical and Electronic Engineers A, 전자수학 A. And I've been teaching this undergraduate course for a long time, and so I have a set of handouts. I little bit modified by attaching some keywords section to each handout. So if you go to my previous homepage, probably you will see the handout starting immediately from section 1.0. You read it, okay? But what I'm going to do is to quickly cover the key concepts and keywords of this chapter 1 today. Okay, so let me ask you a question. What is probability? The problem is this. After many, many years of teaching, I found that even the entry-level graduate students have some misnomer, which means that they use wrong terminology. So let me correct it immediately. So you have to keep these words together in your mind from today. The probability is not just the probability, it's probability of a certain event. So whenever you talk about probability, also remember there follows of some event. So you always talk about probability of some event. There is no probability of x equals 5 unless that x equals 5 is an event. Got it? So you can only talk about probability when you talk about probability of an event. Okay? There is no probability of I am Jo Jun-ho, something like that. Okay? Of course, if that is an event, that's okay. So this is the most important thing. You have to remember or you have to refresh your undergraduate knowledge. So in this lecture 1, I will repeatedly talk about probability of some event, probability of some other event, something like that, okay? And there goes another terminology you have to also remember. Then event is what? What is an event? We have some other modifier or quantifier that limits the meaning of the event. So remember that probability of an event over random experiment. Then next question would be naturally, what is a random event, random experiment? What is a random experiment? Random experiment has modifier random. So probably you want to know, we want to remember what is an experiment. There are two types of experiments as an engineering or science department students you were taught. These two are, one, a scientific experiment. You do some experiment to advance science or to confirm the results of scientific discoveries. There is another one, and which is more closely related to this topic, this subject, this course of random experiment. They too have different modifiers. So they have different meaning, but they have a commonality. They are experiments. Then what are the most important commonalities of experiment, scientific or random experiment? Anybody? That is the repeatability. Of course, some science experiments is very hard to repeat or replicate the results because of the cost or not many opportunities. For example, you do some experiment to observe a supernova. You cannot predict whether there will be a supernova explosion or not. You have to wait a lot of time. In that case, repeatability as a character of a scientific experiment is very, very small. However, if you just publish after observing some supernova explosion, many people may not believe your results. Some people may doubt about your method to process the data, something like that. So usually repeatability is very important and kind of key in scientific experiment. Interestingly, in a random experiment, we are going to talk about a lot in this course, and we did in our undergraduate probability and random processes course, is also repeatability. Without repeatability, probability means nothing. Okay, so here you have to remember this. If you do something related to that occurs only once in your lifetime, forget about probability. That doesn't matter. Okay, suppose there is a tiger that kind of tries to eat you. Okay, you went to a zoo and there was an accident in the cage and tiger kind of escaped and is there. Okay, then what do? You may say that, okay, there is a small probability that the tiger just do not eat me. Never think about that. Okay, never rely on probability theory when you have only one chance. Okay, that's an absurd thing. So what I want you to remember is the importance of repeatability in the probability theory. Without repeatability, probability means nothing. Of course, you may construct a mathematical random experiment and you just try once and once for all. That's okay, because you already assume that that random experiment can be repeated many times. However, you try just once. You conduct the experiment just once. That's okay. Got it? So repeatability is a keyword you must remember. That's what I want to say. In other aspects, scientific experiment is quite different from a random experiment. If you if you perform Googling about scientific experiment, you will see something like, okay, scientific experiment requires hypothesis to test. You have to carefully design your procedure or process of the experiment. You have some control or independent variables and some dependent variables. After also, there should be some objective of goal or purpose of the scientific experiment. And then you analyze the outcome and you reach the conclusion, something like that. However, in a random experiment, that doesn't matter. Okay? What is important in a random experiment is a repeatability first and some outcome. So if it is very hard to define or there is no well-defined outcome, you cannot call that activity as a random experiment. So think about some box. Okay? So you have a box, and this box can generate something that could be observable or that could be unobservable. However, it generates something. Then you may call this output of this box as an outcome. And when you ask that box, hey, generate some outcome, that is called trial. Or so you try a random experiment, you will say, or you conduct a random experiment, or you how do you say it? Yeah, Usually they say that conduct, perform, try, and then you have an outcome. Got it? So it's like something like some box and you just hit it. Hey, generate it. It's like a duck that generates a golden egg, something like that. Okay, probably you remember from your childhood fairy tale, right? Nada, something like that, right? So you, in this case, it may be called a random source. And whenever you ask this random source to generate outcome, it generates something. Interesting thing is that in a random experiment, this outcome has uncertainty. So here goes another keyword, uncertain. Okay? Of course, uncertainty may include certainty. It's like, suppose you have some specifically designed coin that has heads on one side and has the other side. For example, as a magician, you may have a coin that has a tails on one side and the tails on the other side. However, you may also have, to trick the audience, you may have that specific coin. In that case, if you toss that coin, you will always observe an outcome that is the heads, right? In that case, you have a certainty as a magician. That certainty may be viewed as a special uncertainty. So this dealing capability of uncertain outcome may include some certain outcome generator. So it's a kind of generalization of your kind of old knowledge. For example, there is another one. This is called random source. And here is some output, input and output. But this output is not deterministically given by the input. In that case, we may say that this box has some uncertainty, adds some uncertainty in the output. Of course, as a student of high school, elementary school, middle school, and even undergraduate, you've seen some mathematical entity like this, a function or mapping node. In that case, given a specific input x, you have certainty in the output, or in our terms, outcome, right? However, in some electrical systems, most of you, I believe, are electrical engineering graduate students, we have uncertainty because of the imperfection of measurement device, or sometimes because of the uncertainty principle in quantum physics, or some other things, intentional noise, unintentional noise, something like that. In that case, this mathematical model fails to describe what we are going to handle as an electrical engineer. So people have searched for some mathematical entity that helps us to handle uncertain outcome of some, for example, system. And here comes the kind of marriage of electrical engineering and probability theory. That's why we have this graduate level probability and random processes course in the entry level, the first year graduate life of your research assistants. Okay, so sometimes we have source, random source. Sometimes we have a system that adds uncertainty to the output. In that case, we may call this box as a random system, or in communications technology, we may call it a channel, communications channel, something like that. Different academic societies use different terminologies. If you are in communication society, you may probably say that this is a channel. Sometimes you may say that random mapping, some other terminologies you may use. But what is important is that there is uncertainty. So Here goes the keywords. Let me repeat. Probability of an event and event over random experiment. However, I haven't yet talked about what is an event. I talked about outcome, right? Then what is an event? In order to talk about an event that is related to the outcome of a random experiment, we have to rely on the set theory. Fortunately, it's not like mathematics department's set theory. It's like high school set theory. So don't be panic. Okay. What we need is something like that. First, we collect, suppose we only focus on this random source. We collect all possible outcomes of a random experiment and then put it into a set S. By the way, this outcome sometimes called a sample. Okay? And collection of these outcomes, samples, is called a sample space. So what is a sample space? Collection of every possible outcomes of a random experiment. Just simply think about that at this moment. So if you toss a coin, heads and tails will comprise this sample space. So coin toss. If you roll a die, then you have the sample space consisting of 1 to 6, right? And some other sample spaces are possible. And then what is an event? Just remember that. Probably in your elementary school or middle school, you talked about some probability of event like this, even though you didn't specifically, precisely use the terminologies. When you toss or roll a fair die, what is the probability of the event that the outcome is an even number, right? Then you say, hey, it's 1/2, right? What is the probability of the event that you observe a prime number? Then you have prime number 2, 3, and 5. So you may say that, okay, again, that probability of event is 1/2. Sometimes you talk about the probability of an event that the outcome is less than 1. In that case, you may say that the probability is 0. Sometimes you are asked to find the probability of event that the outcome is less than 100. Then the probability of event is 1, right? So what is an event? When you talk about a set called sample space. An event, let's say, let me use capital letter. Suppose A is an event given this sample space. What is that? A is a subset of the sample space, right? So you talk about the probability of a subset of the sample space. So your probability as a function, okay? Let me show that your probability is a function of mapping rule. Then probably you remember from your high school, elementary school math, you use some notation like this, okay? What does that mean? F is the name of the function. After colon, you put the name of the set. What is that? It's a domain of the function. And then you have a right arrow. And then you have another set. What is that? That is codomain. Okay? Sometimes it's called range. Okay? Codomain or range. Similarly, you may now view the probability as a function. Okay? So before probably you say that probability that outcome is blah, blah, blah. However, in some notation, you may have seen something like this. Then definitely P, the probability, is now viewed as a function. So let's follow the same notation. The probability is what? A set function. What does that mean by a set function? The argument, the input of this function P is a set. Of course, in this case, a subset, which is a set of the sample space, right? So what is the domain? What is the domain? That domain is a set, contains events, right? So let me use notation E, calligraphic letter E, and this is an event space. What does that mean by an event space? It's a set consisting of events. You want to assign some numbers through this probability function. Of course, this function is called probability measure, as some of you were taught in your undergraduate probability course. What would be the codomain or range of the probability or probability measure? As you've learned in probability, there is no number, no probability less than 0, no probability greater than 0. So you may want to say that, okay, my codomain or range of this probability measure is the interval of real numbers between 0 and 1, including the values and points, something like that. Of course, when we talk about the codomain, we may replace this one, this interval, closed interval, using a bigger set. Like you may just say, okay, it's a mapping rule from the event space to a real number. You may say that. Because anyway, this number will map any event to a number between 0 and 1. Okay? So this is a review, right? You've learned this. So probability of an event is what? Precisely speaking, you have a function. You think about some function is there. Now consider this. Suppose you have two dices, okay? One is fair and the other is not fair. So this one has something like probability of your outcome is 1/2. And then the others share the other outcome, probability 1/2, right? Evenly. And this one is fair. Then this random experiment, the random experiment tossing or rolling this die has some probability measure. And the other random experiment rolling or tossing this die has different probability measure, right? They map the same, for example, same event for a different number. So each random experiment has its own probability measure. Got it? And that probability measure differentiates, makes the, here is not the differentiation of calculus, make them different when we talk about the probability of some event. Got it? So quickly review the terms again. A sample space, an event, and an event space. Okay. By the way, some of you were taught in your undergraduate course of probability that event space must be a sigma algebra of the subsets of the sample space, something like that. And at that time, highly likely your professor said that, okay, even I do not completely understands this terminology, or even though I know he or she know the meaning, I don't want to want you to be threaten you to drop this course, something like that, and just move. So let me show you some simple results. When the sample space is a countable set, which means that you can find a mapping from this set to a natural number. So for example, this is a countable set, right? there are 6 elements in the set. If you have a countable set, then you can define some set denoted by this one. This is called the power set, of S. And this S should be a countable set, especially a finite set most of the times. By the way, countable set and finite set is a little bit different. Finite set is a countable set. However, you have the maximum number. Okay? So finite set, so that this set is a countable set, at the same time it's a finite set. Okay? So suppose this is the collection of all sets. Then this very small, it should be very small, is a countable set. The collection of all countable sets, and you have a very small subset, a finite set. Okay? By the way, all these complement set is uncountable sets. Anyway, what is the power set? Power set consists of, it's a set, the set consisting of all subsets of S. So given this exponent, a set, you find all the subsets of that one and put them together into the set denoted by 2 to the S. Now let's do some exercise. So given this, please give me all the elements of this power set. The first one is the so-called the empty set, right? This is called the empty set. Sometimes some professors, some textbooks even, do not distinguish the two terminologies, null set and empty set. I hate that, okay? Because empty set means that there is no element. However, in an advanced math book, not all, null set means something different. Okay, so I will just say an empty set or the empty set when the set has no element. Okay, so first, empty set is an element of the power set given this sample space. Then what? You list up all the subsets containing a single element. So 1, 2, ... up to 6. And then consisting of 2 elements, 1, 2, 1, 3, 1, 6, 2, 3, 2, 6. And eventually, you will have the set S, right? By the way, you've seen this in your high school exercise books, right? When you are taught the set and logic and conditionals. And one of the questions was this: how many elements does this power set has? How many elements? It's not that difficult. How many elements? It's 2 to the 6. Because you have 6 elements in the set, and in each subset, this one may be either included or not. Either included or not. So you have 2 choices for each element, and there are 6 choices. So 2 to the 6. Actually, that is the reason why, right? That is the reason why we have, or people have introduced this strange notation. Got it? So actually, this result has motivated this notation of the power set. Got it? So if you have, now let's go back to our random experiment description. suppose you have a finite sample space. So your sample space is finite, such as coin tossing experiment, die rolling experiment, etc. In that case, you can just assume that your event space is the power set of the sample space. No problem, without hesitation, okay? However, here lists why we introduced the notion of sigma algebra, because if our sample space is an uncountable set, then the power set of an uncountable, of course, we can define the power set of a countable sets, like power set of all natural numbers. It's okay, well defined, okay? However, if we talk about the power set of uncountable sets, people have found, mathematicians have found that it's no good. It's not good to precisely define the probability of any event in the power set. They have successfully constructed some strange examples. Mathematicians say pathological, 병적인, in Korean, pathological cases they have found. Okay, so if there is a problem, there is a solution. So they decided to talk about only a subset of the power set. Okay, so given an uncountable sample space, of course, there exists corresponding power set. However, among elements of the power set, you select some of them only, and then you call that as an event space. However, that selection should satisfy something called, in non-technical terms, closedness under countable combination of set operations. This is somewhat strange, and when I was a graduate student, of course, I was not a student in math department. I was an electrical engineering graduate student. Almost every thesis advisors, your 지도 교수, asked, of course, in communications and controls and signal processing area, you to take 2 courses in the math department. One, real analysis or mathematical analysis, in Korean, 해석학. Second, measure theory, 측도론. Of course, I had to take, and in that class, that notion was taught. And I still remember something like that. So what does that mean by closed under countable combination? So you choose some subsets of the sample space and construct an event space for your probability function, the set function, right? You have to have some domain of this set function in order to talk about the probability, right? While doing that, they've decided to choose something like that. What does that mean? Suppose an event is an element of your event space. Then here closed means that apply a set operation to this single event. What do you know? Complementation, for example, right? There are many set operations, but not that many. First one is complementation. It corresponds to, in logic system, negation, right? And there is intersection corresponding to AND operation. Union corresponds to OR operation. That's all, right? So you can apply set operation because you have only one subset, complementation. And closedness under countable combination of set operations means that given A, this must be also in the event space. So when you construct an event space, if an event is in the event space, its complement must be in the event space. Let's go back to our finite set case. Okay? So Suppose you have a finite sample space. This case. See this power set. Empty set has what? Its complement, the sample space, right? So these two are included. Good. By the way, what is the complement of this set containing only one? The set containing 2, 3, 4, 5, 6. And there, right? So this power set is what? Closed under complementation. What if you have two events, A and B, in the event space? Now you can do a lot, right? Because you can complement the event A, you can complement the event B, you can consider the intersection of these two, you can consider union of these two, or you can consider A intersection B and complementation, something like that, right? Of course, you have some choice. So you either have A or A complement, you either or B complement, and you either have union or intersection, something like that, right? Intersection and union. And all these results must be in the event space. Now let's check. Suppose you intersect these two. The empty set here, right? Suppose you take union of these two, where it is here, something like that. So in our finite sample space case, what? The power set, this power set seems, we don't know yet completely what is sigma algebra, but it seems it's a sigma algebra of subsets of the sample space. So usually what theorists do, whether he's a mathematician or electrical engineer, they first consider a simple case, like a finite set or countable set. And they find something wrong with the counterpart, like uncountable sets. What can I do? What they do is that they devise a new concept that in our simple case reduces to what we already know or includes what is already satisfied. So sigma algebra, the notion of sigma algebra is a kind of includes, right, this power set notion when we have a finite sample space. However, let me be specific. Given a countable sample space, you don't need to have the power set as the event space of your probability measure. In some cases, you may only be interested in whether your outcome is an even number or an odd number given a strange, unfair coin. In that case, if you are interested in only in that events, you don't need to fully construct your probability measure, P, probability function P. You just need to construct or derive the probability measure that is well defined in the sample space. However, the event space may contain only what? Only four events. What? The empty set. By the way, by definition, the sigma algebra must contain the empty set and the original universal set. Okay, so empty set and the sample space and two subsets. One including only even numbers, the other including only odd numbers, something like that. Got it? That's okay. Usually we list all the probabilities and all the events. That is sometimes unnecessary. That's what I want to say. Anyway, so what is important is that for an uncountable sample space, we do not, in many cases, think about the power set as our one event space. We just choose a sigma algebra of the subsets of the sample space, which is closed under any countable combinations of set operations, intersection, union, complementation, something like that. Okay, got it? Then what? Then here goes the notion of probability space. So what we do is like this. Here you are given a random experiment, which means that there is an outcome of this experiment, and there is uncertainty in this outcome, right? And there should be repeatability in some sense, at least conceptually. Then how do you mathematically model this random experiment? What you do is this. You first consider the sample space. You choose the event space, and you specify the probability measure. Then that's it for this random experiment. A complete mathematical modeling is done. Okay, so this is what we've learned. Of course, we mostly forgot. I remember, I understand. When I was a graduate student and entered into the first class meeting of probability and random processes in the first semester of my graduate in 1995, fourth semester, I was shocked because my undergraduate probability and random processes, and also I took probability and statistics course, as most of you did, never talk about sigma algebra, never talk about some problem of an uncountable set. They never even talk about what is the difference between finite set, countable set, and uncountable set. They never gave me examples. For example, what is a good example of an uncountable set? You already know, the set of all real numbers. What is a good example of a countable set? Of course, natural numbers, rational numbers. What's the difference between countable infinity and uncountable infinity? For example, here, this set has countably infinite elements. This set also has countably infinite elements. These two sets has uncountably infinite elements, something like that. And I believe one of the most important notions you have to know after you take probability course or even some statistics course is that you know the difference between a finite set, a countable set, and uncountable set. Of course, a finite set can be, is always countable. Okay? I didn't say countably infinite, right? There are two infinities mathematicians has discovered so far. One is countable infinity, and the other is uncountable infinity. Got it? Anyway, so this sample space can be a finite set, a countably infinite set, or an uncountably infinite set. This sample space can be a power set if the sample space is countable or finite, or a sigma algebra of the subsets of this sample space, especially when the sample space is an uncountable set. What is P? The probability function or probability measure. Of course, we never say that what is the probability measure of some event. We just say what is the probability of the event of that argument input of the function. So this probability function or probability measure, as I told you, is defined on the event space we have chosen. Okay? And its codomain is usually a real number, or you already know that this range is 0 to 1. But anyway, let's say R. Then any function, any set function on the event space can be a probability measure? No. Because our logic, because set theory is what? The theory of logic, right? When we talk about logical circuits, we talk about AND, OR, XOR, NAND, NOR, something like that. They all are related to the set theory. Complementation, union, intersection, or something like that. So we have to construct our, choose our probability measure that does not have conflicting results. For example, Suppose you have chosen some arbitrary P for the sample space, heads and tails. Probably you want to have something like this. Probability of heads is 1/3. Probability of tails is then 2/3, right? That is your kind of common sense. No arbitrary number between 0 and 1 can be assigned. For example, 1/3 cannot be assigned. So not every step function that maps a sample space to the interval 0, 1 can be a probability measure. People have tried to kind of extract the essence of what a probability measure satisfies. And that is what? The famous 3 axioms of the probability. Actually, 3 equations, equalities, a probability measure must satisfy. That is usually called 3 axioms of probability. What are they? What are they? The first one is the non-negativity, as I listed here. 3 axioms of probability. One is non-negativity. What does that mean? Actually, we don't need this one. Let me just delete it. That is, just a second. Yeah, that is unnecessary. Let me delete it. Because this actually does that. Okay. So first one is the non-negativity. First, I said that a probability measure is as a function has a codomain R, right? So it seems so far it could be negative something, but first axiom says that its image of the event space must be what? Must give you a number greater than or equal to 0. That is non-negativity. I didn't say positivity. It could be 0. So for any event, if you evaluate that event using the probability measure, your probability of this event must be greater than or equal to 0. It's kind of obvious. We just agreed to use the term probability to have this kind of result. There is no probability of negative million, right? Second one is bounded. Bounded, but interestingly, we know that our event space includes what? That is a sigma algebra, but sigma algebra requires to include the empty set and the sample space. So we can always talk about probability of the sample space. That is one. Okay. And then we have something strange thing. That is called countable additivity. What is countable additivity? Yes. Countable additivity is like this. Suppose you take countable number of events from the event space. Means that you have some sequence of events. They could be the same. Some of them could be same. Okay? So you number these events. So you have, just a second, parenthesis is. Okay? So you have union of these countable number of events. Okay? So A sub 1 union, A sub 2 union, A sub U union. And then, what did I say? A sigma algebra must be closed under any countable combination of set operations. What does that mean? If these A sub n's are events from the event space, then this union, because this is a countable combination of set operation, it must be an event, right? So you can evaluate the probability of this event. Now, we have another condition. No 2 events have common element. This is called mutually disjoint or exclusive, mutually exclusive. Okay? So no intersection at all. In that case, this probability is very interestingly becomes the summation of a probability, each probability of event. And you may say that it's obvious. Why? It's something like this. Let's consider our simplest case. Suppose we have we want to compute the probability of events that something like this. Then what? This is union, 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 right? And each event, so you roll a die, you can never observe you can never observe an outcome that is 1 and 2. You can observe the outcome that is 1 or 2. That's okay, right? But there is no event 1 and 2. You cannot observe 2. What does that mean? This event is mutually exclusive to this event. And if you choose any 2, they are mutually exclusive. Now, what does this mean? This can be written as, according to the right-hand side, probability of event 1, 2, 3. And if it's a fair die, 1/6, 1/6, 1/6, so you have 1/2. Actually, this third countable additivity, seemingly formidable in the first glance, is our what? Our common sense, glorified for the general theory. Okay, so countable additivity, that means what? Union, the probability of the union events of mutually exclusive events is the summation of individual probability of events. Got it? It's obvious. And these properties must hold for any what? For any countable combination of set operations. Because our event space what? Consists of events that are closed under any countable set operations. Got it? And that is the theory. And that is the message I wanted to convey. So from now on, whenever you talk about a random experiment, what is the mathematical model? Your answer is a probability space. Here you may say that, oh, wait a minute, what is a probability space? You said a sample space, you said an event space, you said a probability measure. What is a probability space? This triplet, that thing consisting of 3 things, which usually calls triplet, right? Duet, doublet, triplet, right? If something consisting of 2 things, we say doublet or duo or something. If something consists of 3 things, we say it a triplet or trio, something like that, right? This triplet is called a probability space. So a probability space as a mathematical entity consisting of 3 things is used to mathematically model a random experiment. That's the key. That should have been taught in your undergraduate, high school, middle school, elementary school, math, or probability courses. And I just remind you of this most important thing. Okay? So a random experiment that has an uncertain outcome at each trial or performance or conduct, you model it mathematically using a probability space consisting of the sample space, the event space, and the probability measure. Got it? Now, this is not all. Something interesting occurs. Given now a random experiment and your mathematical model, the probability space, you can define other probability spaces called using conditional probability measure. You can derive so-called conditional probability measure. Interestingly, it's like this. See that? You have a random experiment, so you have a triplet, a probability space having S, E, and P. Now from this event space, you choose an event that has positive probability. which means that you choose a non-null event. This is not important. What is important is the probability of event A is positive. You choose some event A from this event space and evaluate this probability measure P, and it's positive. Now, you can define another probability space. Now, it has the same sample space, same event space, not necessarily, but some event space, and something new. Be careful. This, I just used the notation P of something given A, but actually you can just say this as Q, some function Q, because you have P and you have Q. And if this function Q defined on this event space satisfies the three axioms, you can call this Q as a probability measure, right? That is our consensus. That is our agreement. If you are given a sample space and event space, and if you define a function on the event space that satisfies three axioms, then you can call that function, the set function, a probability measure. Now, we define some new function defined on the event space like this. See that? Suppose you choose some other event from this. It could be A, but you choose any event from this event space. And now you plug into Q. So Q of B. That is actually defined as this one. So see that? We have already chosen A. P of A is non-zero, means that you can put it in the denominator of a fraction, right? Now, you compute set intersection of these two and evaluate using this probability measure and divide by this probability. Now, what is this? It's a real number, well defined, right? Suppose you change this B. You choose any event, then this changes and you have some number, right? So it seems that the Q, the new function defined on the event space, is a set function, well defined, right? It could be zero if the numerator is zero, but it never have some problem of divide by zero problem because we already assumed it's positive, right? Now, what we want to do is that we check whether this Q function satisfies three axioms. So let's see. What is Q of, by the way, is this greater than or equal to 0? So first one is positivity, right? Non-negativity. Non-negativity. So let's check. Is Q of something always positive? And what is your answer? Yes, because, see that? This is non-negative, right? And this is also non-negative. Why? Because P satisfies non-negativity. So we are done, right? 2. Boundedness. So the question is, what is Q of the sample space? And by definition, this is P of A intersection S. Now, what is A intersection S? When S is the universal set, is A. So, okay, is Q equals 1, and your answer is yes, right? So second axiom is satisfied. Third one, countable additivity. So now suppose that the events, sequence of events, are mutually exclusive. So AM intersection, or sometimes they simply call AM cap AN. Okay? Union looks like cup, so cup cap. So AM cap AN equals empty for all M not equal to N, right? And now what you want to do is to check whether this is correct. Right? So let's see. So from the left-hand side, what do? We use the definition. P of A intersection what? Then this one. Union, countable union of AN. Now, what do we do? We have what? The rules, the results from the set theory. What are these? What is the intersection of union? How can you write this one? Whenever you have something looks complicated, simplify and visualize. Got it? So let's simplify. Suppose we have just two subsets. So in this sample spaces, you have A and you have A1 and you have A2. What does that mean? You have here A intersection, A1 union A2. But you know that these two must have no intersection. So when you draw it, you must draw something like this. Got it? So A1 intersection union A2 is this one. And then you intersect. Then you have only this one. So it must be union of, you can guess, A intersection AN. Got it? You know that, right? You just need to confirm what you remember. In that case, just simplify and visualize. That's it. Now, what do we do? Something interesting happens here. Each intersection, right? Let's call this as B sub n. Then B sub 1 and B sub 2 are mutually exclusive. So from the axiom, third axiom for probability measure P, we know that the above, the numerator is simply what? Summation of probability of each event. Now you take this summation out, then you have what? So we are done because this is Q of A sub n. So just simply choosing one non-null event from the given probability space, you can construct a new probability space. Is that all? It has some implication. And you already know that. What's the name of this one? What's the name of this new probability measure Q? And why do we use this notation? This notation. Instead of naming it Q, usually if this is P, we follow the same name P, and we put this bar and we put this event here and call this as what? The conditional probability given event A of what? Some other event, say B. So we call this, we read this notation in this way. The probability of event B conditioned on the event A, or the conditional probability of event B given A. Now, why? Why? Because it has the meaning like this. Suppose this is a sample space, and you have event A and event B. Then what does this mean? This means that given PA, probably entire thing, what is the intersection? This one. So it's like, if you just consider statistics, suppose this is the students in class A, right? And these, these are people, yeah, it's kind of if you have just people in a ground and you just put two circles and let the people stay there, then what does this mean? This is the ratio of people in the intersection given this number of people. So given A, right? Given A, how many people satisfies the condition of B? Something like that. That's why we call this probability measure as the conditional probability measure. Now, Can you find other conditional probability measures? Yes, you can. You can choose any events from the event space, given the probability space, and you apply any countable set operations to have an event. Then, using that event, you can construct a conditional probability measure. So, if you have an uncountable sample space, for example, or you have countably infinite event space, for example, then there could be many, sometimes infinite number of conditional probability measures you can define, given a single probability space. That's amazing, right? And of course, that's amazing for professors because they can make a lot of new problems, right? So this is the idea. Now, so we have defined the conditional probability measure, and there was something interesting. So whenever you have some ratio, okay, alarm must ring, right? Must ring. Hey, divide by 0 is not allowed. Suppose we multiply to both sides P of A. Does this hold? Of course, it's definition, and we multiply non-zero number because we assume the P of A is non-zero. What happens? We have something like this. Here we have A intersection B equals which one? This one, right? P of A times P of B given A. Now we can just, because this is same as that one, because in the intersection there is no order, right? You can change and they are the same. So here you just replace A with B and B with A and you have that. What does that mean? Now we have so-called a chain rule. When you want to compute the probability of the event of some two sets intersected. So intersections event probability can either be written as what? This is called unconditional probability of event A and the conditional probability of event B, or conditional probability of event A times unconditional probability of event B, right? So this is very, very useful trick when you compute some probability of the intersection of two events. Because sometimes direct computation of this probability of event is very difficult. However, what you do is this. You just consider a small set, okay, like this. Okay, let me consider some this set A, okay? And it seems that it's not that difficult to compute the probability of event A. Now, what you do is that you compute the conditional probability of event B given this A. Suppose that's easy. Then you multiply these two to get the probability of this intersection. Or you may find that finding the unconditional probability of event B is easy. And also, at the same time, computing conditional probability of event A given B is easy. In that case, you use that one to compute the probability of intersection. That's very, very important trick. And actually, you have been using this chain rule in many exams, homeworks, and probably in the future in your research. Okay, so this is a chain. But one interesting thing is this one. Okay, here you see some symmetry, right? Due to the fact that A intersection B equals B intersection A. What if I divide both sides by that one and also that one? Then what you have is something like this, right? See that? If this goes to the denominator and that goes to the denominator, it's like probability of conditional probability of event A given B divided by unconditional probability of event A equals conditional probability of event B given unconditional probability of event B. And we've seen something similar. This definitely is a positive real number, right? Non-negative real number. That is the notation. What else can you say? Is it always greater than 1 or less than 1 or equal to 1? Actually, depending on how you choose the events A and B, this ratio, even though they are always the same as far as P of A and P of B are non-negative, they are always the same. However, it could be greater than 1, less than 1, or equal to 1. What does that mean? See that? Let's see the left-hand side. What if this is greater than 1? It's like this. The unconditionally probability of event A is some number. Now you consider the case where some event is happened already, occurred already. Then is that fact, event B occurred, affects the probability of event A? That is the question, right? And that could be greater than 1. What does that mean? Occurrence of event B increases the probability of event A occurring. Same thing happens, right? Sometimes it could reduce. Sometimes they keep the probability and conditional probability the same, right? It depends on the situation. Sometimes it's like this. You've met some people, right? And you have some value of that person. It's a good candidate for my girlfriend, something like that. And you receive a katalog, and there are some grammatical errors. And usually after that event occurs, usually your how do you say, your score reduces sometimes. Then that thing, that grammatical error affected your motion, right? Emotion. Sometimes it could be, does not matter anything because you also makes a lot of grammatical errors, right? So it could be greater than 1, less than 1, equal to 1. Now, equal is something special, right? Greater, less is not that special. It could be happen, but what if they are equal to 1? What if this is 1? What does that mean? Again, you move that one up and get something like this. Given two events, the probability of event A does not change whether the event A occurred or not. It doesn't matter. And you want to call this special case using some terminology. What is that? They are independent events. Okay? So the notion of independent events kind of naturally derived from the definition of the conditional probability measure. And we are going to talk about that later in this Thursday. And it seems we have a big problem in order to this course to become a regular course offered. We need 5 students, but it seems we have only 4 today. So let's see what will happen in this Thursday. And if we have still less than 5, we have a serious problem. Okay, that's all for today.